So we're going to let v in component form be the vector -4, 2, 5. U in component form is 10, -3, 8. Let's find 2u minus 3v. Which operation do you do first? Multiplication or subtraction? Okay, so multiply. So 2, let's see if we can do this in our head. Oh, look at the right thing. I almost looked at the wrong thing. 2u, what would 2u be? 20, -6, 16. So there's 2u. What would, okay, then minus in between them. What would 3v be? Just triple everything in v. That's how. So -12, 6, 15. Right? Scalar multiplication, we call that. And then we're going to go ahead and subtract component-wise. So we're going to have 20 minus a -12. So 30, so 20 minus, so we have a minus here and a minus here. 20 minus a -12 would be 32. Does everybody see that? -6 minus 6. -12. 16 minus 15. Don't do that, you make me yawn. So 16 minus 15 is 1. Okay. Everybody. Do you think finding the magnitude is going to be a whole lot different? No, because of the distance formula that we've developed for the distance between 2 points. You can essentially use that to have a kind of a three-dimensional version of the Pythagorean theorem, which gives us the length of a vector. So that notation, either double bars, you'll see in Stewart, I think, uses single bars, but some books use double bars, and it means the length of the vector. So how do you find the length of the vector? You find the distance between the origin, which is going to be the tail, right? And the tip, which in this case is -4, 2, 5. It's essentially the distance formula. So that magnitude of v is going to be the square root of, okay, are you going to bother putting in -4 minus 0? No, it's just -4 squared plus the first component squared plus the second component squared plus the third component squared. But it really is just the distance formula, which is kind of a version of the Pythagorean theorem, except in space. So what is that? 16 plus 4 plus 25 square root of 45. I don't know if I can resist simplifying it. Can I resist it? Yeah, I can resist it. In other words, I know you guys can simplify that. I'm not going to waste time on it. IJK form. Okay, I is the vector 1, 0 in the plane, right? J is 0, 1. Well, in space, then, put in a third component, and I becomes 1, 0, 0. J becomes 0, 1, 0. And we need a third one, K, 0, 0, 1. And it turns out you can write any vector as what you'd call a linear, if you've had linear algebra, you'll recognize this term, a linear combination of I, J, and K. These are called standard basis vectors. And it really doesn't matter that I'm using 8, 5, and 3. I could use A, B, and C and do a very similar thing. You can write 8, 5, 3 as 8, 0, 0 plus 0, 5, 0 plus 0, 0, 3. I don't think there's anybody who'd argue against that unless you're tired, right? And cranky. Unless you're tired and cranky, I don't think you'd argue that, right? And then so that's kind of undoing addition. Using scalar multiplication, I could rewrite this. This first one is 8 times what? 1, 0, 0, which is I. The second one is 5 times essentially J, right? 0, 1, 0. And then 3 times K, which is 0, 0, 1. So I'm just kind of showing you why you can write any vector in the form in the I, J, K form. And that you shouldn't be afraid of I, J, K form. It's actually a really nice form. So you could rewrite this as 8I plus 5J plus 3K. So if you want to pick out the components, you just look, 8, 5, 3. If you want to change it back to component form, right? Now, it really irritated me when I was in your shoes. Why do we have two different ways of representing the same thing? I like component form. If you watch the video, you know that IJK form is superior when you're doing algebra, when you're doing operations on these things, because it looks like algebra. So we're gonna do the last example over again, but we're gonna do it in IJK form. So, okay, let's use a sort of substitution. So you're gonna go ahead and put 10i minus 3j plus 8k. You're gonna put that right in for u, aren't you? Parentheses around it. And you're going to put v, negative 4i plus 2j plus 5k, right there for v, right? And you get 2 times 10i minus 3j plus 8k. That's the 2u part. And then what's the next part? Minus 3 times, well, v. So that's negative 4i plus 2j plus 5k. Does everybody see what I'm doing? And then you do the scalar multiplication first. We've done this example already in component form, right? You do the scalar multiplication first, but then what operation does it look like? Or what law does it look like? Distribution. That's the beauty of it. So it really is scalar multiplication, but it looks like distribution from algebra. So what do you get? We'll even use the same kind of thing. Oh, yeah, point at all those, multiply them all by 2. 20i, finish it off for me, 20i minus 6j plus 16k, right? You got to include that operation. And then subtract off 3 times that vector. It looks like it's scalar multiplication, looks like distribution. What do you get? Include the operation. Plus 12i minus 6j. All right, you guys are getting in sync now. I like that. Minus 15k. What's the next part look like? Adding like terms. I feel like I'm selling you this stuff. This is great notation. It looks like something you're really familiar with. So, okay, so add corresponding components. Add I components together. What do you get? 20 plus 12i, 32i. Add j components together. What do you get? Negative 12j. Add k components together. So just plus 1k or just plus k is fine. And you do get this 32, negative 12, 1, exactly what we got. Where was it? Up here. 32, negative 12, 1. It's the same thing, different notation. And it is kind of better in the sense that you don't have to remember anything. I mean, if it's an IJK form, you just do operations that you've been taught since beginning algebra. So did I sell it to you? Do you believe me now? So nobody sold it to me like that, so I hated this stuff when I was in your shoes. I wanted to be in component form all the time. And component form has its uses, don't get me wrong, but when you're doing lots of operations like this, I think IJK form is better.